Hi, I'll now explain to you certain things about rainbows and such as, basic ideas how the rainbow is formed and stuff like that. Hopefully some ideas so there aren't that much overlap with stuff by other people. Here it goes. Alright, first up, a rainbow, as you could see in the great lectures by Walter Lewin, it's basically it begins this way. You have a water droplet, sunlight comes in this way, all the dotted line, all the sun rays are parallel, right? So they hit the sphere here, the water droplet, at various incidence angles, and they get refracted inside the bubble, right? And you always notice that the rainbow's behind you, so the main rainbow is usually the result of just one refraction inside that. Usually not always, pretty much one refraction inside the bubble. Okay. Here I drew it a little bit bigger. The same picture right here. Sorry, the same picture right there. And you notice something, that the light comes in. Let's say it comes this way, right? Because that's the direction that all the sun's parallel rays are hitting the water droplet, and then they end up getting refracted and end up coming out that way, right? Now if you notice, if I continue this here like this, right, and make a line that touches right there, this line in the middle, right, that's sort of reminiscent of some kind of a vector relation that's shown right here in this green thing, right? So this direction vector is the direction that the light is incident in, and this is the direction vector that the light is refracted in. Now, one thing is this: all the rays come in right in the same direction, but they're refracted in various directions, right? But at the end of the day, though, right, there's like some limit directions that they're refracted at, and at that limit direction, that the light there is very strong. So let's say that light comes in this way, right, but it's refracted this way, right, that way, whatever, this other way, but there's a certain limit somewhere around here, let's say, right, beyond which is not refracted, and right at that limit is basically where most of the rays that are refracted get concentrated in that direction. So in other words, there's like a preferred range of little directions here where the light is very strong. Okay, so let's say this was red light that came in like this. That at a certain angle there's a lot of red light that's going to come out that way. Basically at a certain direction, there's really a small range of angles or directions right there, very near that one. Okay, the same thing will happen for any other color, right? And again, since the sun's rays are parallel, again blue will come in this way, right? They don't have a maximum angle, but the angle will be, let's say, smaller. So the angle at which blue will be strongest will be somewhere, let's say, in this direction. Okay, so then so you have basically different directions where different colors are strongest. So instead of drawing this drawing though right here, right, let's flip the direction of the incident vector here, and let's point it this way, just I don't know, to make it visually simpler. Then what you get here is basically a cone, right? Because this happens in all directions around this way, like this. If I spin around that direction right there, notice the opposite of the incident direction of the light there that I wrote, and so that really makes a cone. And here I've drawn the cone right here. Now this cone is really like a hypothetical object, right? Because the light just comes in here and comes out here, right? But if you extended it like this, and then you could think of that as sort of like the cone of directions that the light emanates out. So you have this cone here. I've drawn the actual cone. Here I've drawn the actual cone. So you have so you have the cone right here, and this point right here is the center of the bubble. So over here, the same story that we had here, that bubble had a center, or that droplet, sorry, had a center. Well, that right there is the center of the droplet. Now it turns out that if the droplet was bigger or smaller, the angles would still be the same, except that in relation to this cone of directions, the center of the bubble will be at a different place. So this second little dot here that I put here, that's sort of like to represent, you know, the case where you have a let's say a smaller where is it? Hold on, this pen is going everywhere. There you go. Okay, that right there would be the center of a smaller bubble producing that cone of light, and this one would be, you know, the center of a larger bubble, you know, with light incident in the same direction, which is this center axis right here of the cone. So that's what would happen. So basically, you could say that at the end of the day, when parallel rays hit a spherical water droplet, what ends up happening is that you get this thing that's like a cone of light, and this again for each how could I say this, for each different color, right? It'll be, you know, a slightly more opened up or more closed up cone. So maybe for, let me see if I can draw it here for you. Let's say for blue light, you'd have a cone like this, right? Sort of like a thinner cone right there, like that, right? And for red, it would even be, you know, thicker, fatter cone. So it's like a bunch of nested cones, red and yellow, you know, then green, then blue. Okay, all right. So that's what it is. So you have that. So each droplet produces this this cone, and this little dot right here, which, you know, how far out it is, how far along in this center axis it is, depends on the size of the droplet. But that right there, that little point will be where the center of the droplet is. So each droplet will produce a cone like that of light, of different colors, and the center of the droplet will be, you know, somewhere there. I did two possible spots of two different size bubbles, but it'd have to be, you know, either or, one or the other, right? Either you have a big bubble, a big drop, or a small drop producing it. So it would be just one of those. All right. So now what happens after that? So again, each drop will produce a cone of light, like so, centered right at that point in the drop. Okay, with the center of the droplet. All right. Now imagine this is your eye right here. Okay, so that little green dot right there is your eye. Now light comes from one of these droplets and goes into your eye, right? Well, let's say this for specificity. Let's say red light goes into your eye. Okay. This light, red light that is produced by one of the droplets, right? This light can only come in certain directions. It can only hit your eye in one of the directions of the cone. So if red hits your eye, it could have basically come in this direction, that direction, basically all the directions that are shown in this cone right here. And then let's say that this right here, right, that right there is your retina. So you have this you know, a light, right, incident on your retina, right? So for that, so from that direction, you're gonna get a point, right? But from some other direction, you know, it's gonna be some other a point right here, right, of that cone, etc. So in the end of the day, if you had all the directions represented there, you'd get a circle, because that's where, you know, where the cone intersects your retina. All right. So so now, you know, and each color would produce, you know, the corresponding a cone. So you'd have a family of nested circles, right? You know, red on the outside, that's the wider, then inside, etc. So and this particular model with just a pinhole like that, we could say that that's if your eye was you know, a pinhole camera, or if you had, you know, a pinhole camera taking a picture of the rainbow, basically. All right. So you have that, and now where's the, you know, like where's the rainbow, or rather, like, where are the droplets, right? Well, if this thing got to your eye, right, it turns out that if you analyze it, it could have only come from droplets that were like this, so that were on a line parallel to that line, relatively close, that has something to do with how far from this line right here is this little dot of the center of the droplet, right? That's why the droplet, notice, is a little bit offset from this line. Here the same thing. So if you see that green line, it'll come, you know, from droplets that are slightly above and are in that, on that orange line, along that orange line. And of course, if this thing is blocked, then you won't get any color from that. So maybe you won't see, you know, this piece down here of the circle. Okay. So that's the first thing. Secondly, you may wonder, this, if you think about it enough, you'll notice that this thing really has sort of like no size, or it's nowhere. In other words, as long as you had the sunlight all parallel, and you had droplets, let's say in any of these spots, they could be either here or here, they would produce this image here. So in a sense, that sort of says that a rainbow's got no size, right? But then you go and you on a sunny day, you go with a hose and you make make sure that the sun is behind you, and you make a rainbow with a hose by making a fine spray, right? And then you see a rainbow that to you looks pretty small. But then after rain, you look out into the distance and you see a rainbow and it looks humongous. So, but according to this theory right here, from what I've shown you, both of those rainbows should make the same size ring on your retina. So, or the same size family of nested rings. So, how is it that you distinguish the size of a rainbow? How is it that you ascribe size to a rainbow? Okay. I don't know the exact answer to this, but I'll give you a clue of something. If you just made, let's say you just made a rainbow. Here's your retina. Let me see if I can hold on. Let's see if I can make this a little bit okay. So there's the ring that you see in your retina, right? And let's say that a little bit a distance away from you, there's a tree. Man, I'm gonna have to use blue for this, a blue tree. Okay, but let's say there's a tree trunk. So you see the tree trunk like this. Okay, so you see that the rainbow, it's before, you see it as being before the tree trunk, right? And you see this huge tree trunk. Okay, now say that the other situation. Say that you have, let's say, the same image here in your retina, right? But this thing is being produced by droplets or like that are very far away, right? Okay, so maybe there's like, you know, trees or foliage or whatever in between, right? There's even some washing also by the, you know, like aerial perspective kind of stuff. Let's say that there's some small bush right there in front of this thing. So you know that this thing is like, let me try to cover this piece of it. So you know this thing is basically behind this bush, right? That maybe is the same distance, let's say, as that tree that we had drawn there. Okay. Then on top of that, you're looking in the distance. Now you're seeing a distant tree. So then you say, okay, before this thing was near me, just from the fact that, you know, it's before that tree, right? And it looks small compared to that blue tree right there. So then I say, oh, it's near, and it's small. But if I see it like in this picture over here, where it's covered, you know, by some bushes at the same distance of the tree, then I interpret this ring thing as being very far away, right? And then on top of that, it's very far away, and a tree that I assume more or less to be at the same distance that he is much smaller than him. So I guess from that I judge that this ring is humongous. But yet these two are exactly what the picture in your retina is, right? And you notice that they're both the same size. So that perhaps, you know, helps a little bit to explain this thing. Although honestly, I don't find none of these, you know, like the Terminator paradox and none of these explanations that I've seen online really convincing, or, you know, or the one about the moon illusion, you know. But this one is at least, you know, this argument is at least more, seems more convincing, basically. So hopefully, you know, this will give you some ideas to research. All right, take care.